Hey guys, welcome to CakeWalk Cambridge. I'm Aisha and you're watching IGCSE Chemistry's Stoichiometry. It's basically moles and a lot of kids struggle with this concept, but it's actually really easy and just taught poorly in school. So I thought this is something I'd do. I've decided that from now I'm going to just teach concepts, but this is going to be the last video in Chem where I do like a whole chapter because it is basically a string of logical, easy concepts. And I hope this helps you a little bit. Also, shout out my roommate's sister. She gave me motivation to start posting again, and that's why I'm here. But yeah, I hope this helps you. Let's get started. So we're going to first look at like some basic definitions. So the first one is molecular formula. The molecular formula is basically the number and type of different atoms in a molecule. So for example, if we have a molecule of carbon dioxide, we have the molecular formula of carbon dioxide is CO2, which basically tells you there's one atom of carbon in the molecule and two atoms of oxygen, CO2. So that means CO2. One atom of carbon, two atoms of oxygen. And then we have the empirical formula, which is basically the simplest whole number ratio of different atoms or ions in a compound. Now, if we look at carbon dioxide, it's 1:2. One carbon is to two oxygen. But then if we look, so that is the empirical formula. So the empirical formula and molecular formula of carbon dioxide is the same. And there are many compounds like methane, which is CH4, which have the same molecular and empirical formula. So don't get confused in questions. But then if we look at something like ethene, which is C2H4, that means the molecular formula of ethene is C2H4, two atoms of carbon, four atoms of hydrogen. That is not the empirical formula. That is not the simplest whole number ratio of these atoms in the compound. The empirical formula is 1:2. One carbon is to two hydrogen because it's C2:H4. You simplify that, divide by 2, it's 1:2. Okay, that's basically what it is. Now we'll move on to relative atomic mass. Basically, now this definition looks a little complicated and it is something you'll have to kind of mug up because it comes to like 1 to 2 marks, and there is like no way to get around this definition. You just have to memorize it. But let me explain it to you. So basically, as you know, let's take chlorine, okay, as an element, okay. So now all atoms of chlorine will have the same proton number. They have the same atomic number, correct? Which is around 7, which is 17, okay? But how they differ is in their mass. So basically there is a certain proportion of chlorine atoms with an atomic mass of 35, and there is a certain proportion of chlorine atoms which is with an atomic mass of 37. Now basically what this means, atomic mass is atomic number plus neutron number, proton number plus neutron number. Now the proton number is 17 throughout. That means that there is a certain discrepancy in the neutron number. So that means the neutron number will vary across chlorine atoms, correct? So now to find out but now we can't do calculations of moles with like different masses, right? Every time we're using chlorine. So what we do is we find out the relative atomic mass of chlorine, which is basically an average of the atomic masses present in the environment of chlorine. So what we're going to do is we're going to average the number of chlorine atoms with an atomic mass of 35 and the average proportion of chlorine atoms with an atomic mass of 37. And when you average the two of them based on how much they're present in the environment, what their abundance is in the environment, we reach 35.5. And that is how you know that the relative atomic mass of chlorine is 35.5. That's basically what it is. Easy, correct? Now we'll move on to relative molecular mass. If you have questions, drop it down in the comments. I hope I explained it well, but yeah, it's a little confusing. But when you get it, you'll understand it. Then we have relative molecular mass, which is basically the sum of relative atomic masses. So for example, from our calculations, we have found out the relative atomic mass of iron, Fe, is 56 and the relative atomic mass of oxygen is 16. So basically, when you need to find the relative molecular mass of Fe2O3, iron oxide, what you need to do is understand how many atoms of iron are present, how many atoms of oxygen are present in the compound. And then basically you add the atomic mass of each based on how many times they're there. So for example, iron is 56. That is the relative atomic mass, but it's present twice. So you multiply 56 by 2. And then oxygen is present thrice and the relative atomic mass is 16. So you multiply 16 by 3, you add up the 2 and you get 160. So the relative molecular mass of iron oxide therefore is 160. Now we'll go on to actual stoic, which is, we're going to start with the basic of it all, that is a mole, which is also called Avogadro's constant. A mole is basically 6.02 into 10 raised to 23 particles. That is atoms, ions, or molecules of a substance. So if I tell you I have 1 mole of iron and 1 mole of chlorine, it doesn't matter what their masses are, they are equal. Like 1 mole is equal. 1 mole of iron is equal to 1 mole of chlorine, because that's basically 6.02 into 10 raised to 23 particles of the substance. Now, obviously, the masses of the two will be different, but the number of atoms that they both comprise are the same. Okay, so 1 mole of iron is 6.02 into 10 raised to 23 atoms. 1 mole of iron oxide is 6.02 into 10 raised to 23 molecules. 1 mole of Fe2 plus is 6.02 into 10 raised to 23 ions. It's the same thing. So very often they'll confuse you and ask you like which has more particles, 1 mole of iron or 1 mole of oxygen. It's the same. They have the same number of particles. Okay, that's basically what you got to remember. So now we'll talk about calculating moles and how to find out how many moles there are in a given mass. So now the formula for that in solids is 1 mole is equal to the mass present on molar mass. So for example, if I have like 5 grams of iron present, okay, and I want to find out how many moles there are, the formula for that would be mole is equal to 5 grams over molar mass, which is 56, as we saw earlier. So it's 5 by 56, which is around 0.089 moles. Okay, that is how much moles there are. So let's just do this very, very easy question. So copper oxide, copper 2 oxide reacts with dilute hydrochloric acid. As you can see, CuO here is the molecular formula of copper oxide. The empirical formula would also be CuO, 1:1 ratio. That is the simplest whole number ratio, just some basics. Okay, it reacts with dilute hydrochloric acid. They've given you the equation here. And here they've told you 6 grams of copper oxide was added to 50 centimeter cube of 1 mole per dm cube hydrochloric acid. We'll get to the hydrochloric acid part later. But first we want to find out how to calculate the number of moles of copper oxide. Okay, so we have here 6 grams is the mass, the given mass. Mass means given mass, the mass we're using in the experiment. So we know that 6 grams is the mass. Okay, now we need to find out how many moles of copper oxide are present, okay, in this sample. So what we also need is the molar mass. The molar mass of copper oxide I'm giving you is 80 based on the periodic table. So basically to find out the moles, now you need to divide the mass by molar mass. So what you got to do is divide 6 by 80 and your answer is 0.075 moles of copper oxide. It's as simple as that. Okay, I hope that was easy. This is the standard rule. Mole is equal to experimental or given mass over molar mass. Now we'll go on to moles in solutions. That was for solids, this is for solutions. Moles are basically, a mole is basically concentration into volume. Here you must remember that the concentration in volume, the denominator, how you measure volume is in dm cube. 1 dm cube is 1000 centimeter cube, another conversion that you need to memorize. Okay, so when you're basically multiplying concentration by volume, you need to make sure that both have the same unit. You need to see that it's mole per dm cube or gram per dm cube into volume. Okay, that is dm cube. Both have to be in dm cube. If one is in cm cube, you divide it by 1000 by default and it turns into dm cube. Okay, so now in the same example, we know that there is 50 centimeter cube of 1 mole per dm cube hydrochloric acid. So now to basically calculate the moles present, now I'm going to ask you to calculate the moles of hydrochloric acid present in the solution. What you got to do is multiply the concentration by the volume. So now here we have the concentration to be 1 mole per dm cube of hydrochloric acid and we have the volume to be 50 but centimeter cube. So when you have these units, you should underline them in your paper so they stand out to you. So what you have to do is to convert 50 centimeter cube into dm cube, you need to divide it by 1000. So 50 by 1000 is 0.05 dm cube. So to basically find the moles, now you multiply concentration by volume. Okay, so the concentration is 1 mole per dm cube. The volume is 0.05 dm cube. You multiply 1 by 0.05 and your answer is 0.05 moles of HCl. As simple as that, super easy. Cool, let's move on. Now we need to find out whether a substance is in excess or limiting in such a reaction. Okay, now this is a very common question. Okay, and we're going to go through it. It's really easy once you get the hang of it. Okay, so now this is your question. Okay, we have found out, and now what the question is telling you is that one of the two reagents are the reactants. They are what is on the left hand side of the equation. One of the two reagents are in excess, okay, which means one of the two of them are present in more than what is required, okay, to react. That means there's going to be some leftover of one of the two that is unreacted. Some mass of it, some volume of it will not be reacted in the equation, okay. So how to find this out? So what we know already, we've calculated the moles of copper oxide to be 0.075. That's 6 over 80. And we've calculated the moles of HCl to be 0.05. That is 1 into 50 by 1000. Okay. Now what we need to do is calculate and see which one is present in more than what is required. So now this is the way to do it. So what you need to do in such an equation, okay, is to basically check the ratios of the reagents. Okay, so here we can see copper oxide is present 1, so it's 1 COO, and here HCl is 2, it's 2 HCl. So the ratio of copper oxide is to HCl is 1:2. Okay, so basically for 1 mole of copper oxide reacting, there has to be 2 moles of HCl reacting. So now if HCl was in excess, okay, so basically now we're going to look at hypothetical scenarios. If copper oxide was in excess, okay, CO was in excess, that means HCl would be as it was, that is 0.05 moles, okay. But that means that the moles of copper oxide present would have to be more than 0.025. So basically, if copper oxide was in excess, HCl would be 0.05, and the expected moles, the needed moles of copper oxide would be 0.05 divided by 2, correct? Because the ratio is 1 copper oxide is to 2 HCl. So you divide 0.05 by 2, that's 0.025. So if HCl was in excess, COO would have to be more than 0.025 moles present, okay? And if it was the other way around, if HCl was in excess, the moles of copper oxide would be the same, that is 0.075. And if we multiply it by 2, because it's a 1:2 ratio, we would need 0.15 moles of HCl. And that means if it's in excess, there would be more than 0.15 moles of HCl. Now if we look at these two, okay, look at these two hypothetical scenarios, which one fits the current scene? That is 0.05 moles of HCl and 0.075 moles of CO. Let's look at the second scenario. If HCl was in excess, there had to be 0.075 moles of copper oxide, which is there, correct? But HCl has to be more than 0.15 moles. Here we can see it is 0.05 moles, so we know that HCl is not in excess, okay? But if we look at the first equation, there would have to be 0.05 moles of HCl, which is satisfied, correct? And there would have to be more than 0.025 moles of copper oxide, which is also satisfied. So from this equation, we know that copper oxide is in excess. As simple as that. Now, if they flipped over the question and asked you which reagent is the limiting factor, then that would be HCl. Okay, because copper oxide would be the same and HCl is basically less than 0.15. It's 0.05, that means HCl is limiting. But here they've asked you what is in excess, and here you know that copper oxide is in excess because it's a 1:2 ratio. There is 0.05 moles of HCl, which would need 0.025 moles of CO to react, but there are 0.075 moles of CO present in the solid. So that is more than what is required. So CO is in excess. So now how do we find out how much of the excess reagent didn't react? So what we know already is that the moles of CO are 0.075. The moles of HCl are 0.05. The mole ratio of CO is to HCl is 1:2, which means that the number of moles of CO that reacted is 0.025, correct? Based on this, let's go over this, okay? So the moles of HCl reacting are 0.05. The moles of CO reacting are 0.05 by 2, which is 0.025, okay? So therefore, the moles of CO that do not react are 0.075 minus 0.025, which is 0.05 moles unreacted. We know that the molar mass of CO is 80. We also know that the equation for moles in solid form is moles is equal to, forgive my handwriting, is equal to mass over molar mass. Therefore, the mass of CO not reacting is equal to moles into molar mass, which is equal to 0.05 into 80, and that is 4 grams. So the amount of copper oxide that doesn't react is 4 grams, and we know that we started off with 6 grams of copper oxide. That means 2 grams of copper oxide did react. Okay, I hope this made sense to you guys. Okay, now we're going to move on to calculating moles but in gaseous form. So basically, for a gas, it is the easiest actually. 1 mole of a gas is always 24 dm cube, okay? It is standard. So as we saw, molar mass is varied in solids, but in gases, the molar volume stays the same. So to find out the number of moles present in a given volume of gas, all you have to do is divide that volume in dm cube by 24 dm cube. Okay. So for example, if we have 72 dm cube of oxygen, how many moles? It's 72 by 24, which is 3 moles of oxygen. Make sure that both of these are in dm cube. If it's in cm cube, divide by 1000. Okay. Basically, so now if they ask you the number of particles of oxygen in 72 dm cube of oxygen, what you need to do is first find out how many moles there are of oxygen in 72 dm cube of oxygen. We have found out that there are 3 moles. Now we also know that 1 mole is 6.02 into 10 raised to 23 particles, ions, atoms, or molecules of a substance. Therefore, 3 moles will be 3 times the Avogadro's constant, which is this value, which is 1.8 into 10 raised to 24 particles. This is a very frequently asked question. So always understand when they're asking you particles, you don't have to use masses or anything. You just have your moles and you multiply the number of moles by 6.02 into 10 raised to 23. Okay, that is pretty much what it is. Okay, so now in the next video, we will be solving a couple questions on moles and stuff, and we will also be moving on to percentage purity and percentage yield. But that's it for now. It's been like 17 minutes, which I think is more than enough for one sitting of chem. I hope this video helped you, and if it did, please like, share, subscribe. If you have questions, comment. If you have any like bigger questions that you think I can't answer in a comment, feel free to email me at cakewalkcambridge@gmail.com. My email is on the YouTube page as well. And yeah, I hope this video helped you. Stay tuned for the next part. Let's get through this together.